So let's understand the basics of circles. The standard circle equation is x minus h squared plus y minus k squared is equal to r squared, where hk is the center of the circle and r is the radius of the circle. For example, we have x minus 6 squared plus y plus 1 squared is equal to 81. As you can see, the center of the circle is 6, negative 1 with a radius of 9 units. To confirm this, I will put the circle equation into GeoGebra. And over here we have point A, 6, negative 1 as the center of the circle. And we are going to create a radius. Line segment AB is going to be acting as a radius. And as you can see, segment AB or F has a length of 9 units, which confirms that the radius is indeed 9 and that the center is 6, negative 1. So if we look at our second equation, x squared plus y squared equals 49, you will notice that this equation does not have an x plus or minus value or a y plus or minus value after x and y. This just means that the center of the circle is at the origin or 0, 0 and has a radius of 7 units because the square root of 49 is 7. So I'll put this again in GeoGebra. And as you can see, we have 0, 0, point A as the center, and we're going to draw a line segment AB or line segment F acting as the radius, and that angle AB or segment AB and or segment F is 7 units, which confirms 0, 0 is the origin and that 7 is indeed the radius.
A chord of a circle is a straight line segment whose endpoints both lie on the circle. Say you want to find the length of a chord here where you know that the radius is 5. You can draw a perpendicular bisector right down here, creating two right triangles. Then simply divide the top angle of 70 degrees by 2 to get an angle of 35 degrees on both sides. Down here, you know that this angle is 90 minus 35 degrees, getting you a 90, 35, 55 triangle. With this information, you can use trig to calculate the chord's length. Simply multiply the radius by 2 to get 10 times the sine of 35, and you get your answer, 5.736. The vertical angle theorem states that this angle here and this angle here, the vertical angles, would be equal, while this angle right here and this angle right here would be supplementary. If you have two chords that create an angle, you have an inscribed angle. Inscribed angles are automatically known if you have its corresponding arc length and vice versa. Say you have here on this arc, AC, that you know it is 120 degrees. The inscribed angle theorem states that the corresponding inscribed angle is half of the arc degree measure. So because arc AC is 120 degrees, we can divide 120 by 2 and you know that angle ABC is 60 degrees. The inverse is true as well. Because we know that angle ABC is 60 degrees, we can also know that arc AC is 120 degrees. Now here we're presented with a particular problem with two circles of differing radii. Now from here down to here, I can draw a chord. Since this chord is shared by both circles at the exact same location, this is a common chord. Given to us is that the radius right here of this circle, AB, is 13, and the radius over here of this circle, CE, is unknown. I'm going to label it X. We also know that our chord, given right here, is 24. And we know that the distance between these two circles' centers, shown right here, this is not drawn to scale, is 14. What we can do now is draw right triangles, starting from A to D to G. Draw that one up here. And we can also draw another one that would be from C to D to G. We know that DG is 12, since 24 divided by 2 is 12, and that gives us one side of the triangle. And We know that the radius from A to D is 13. That's going to be our hypotenuse. And by using the Pythagorean theorem, we know that the remaining side of the triangle would have to be 5. On the other triangle, we have our hypotenuse at x, that's the radius, being DC, shown right here. We have our height right here is 12, and our base is 14 minus AG, and 14 minus AG, AG is 5, as seen right here. 14 minus AG equals 9. Now, 9 squared plus 12 squared equals 225. Its square root is 15, and now we have our answer. The radius, shown right here, is 15.
Alright, so on to tangents. What exactly is a tangent? A tangent in relation to circles is a line that only meets or touches a circle once at its circumference. This makes the radius of the circle perpendicular to where the tangent meets the circumference of the circle. So let's take a look at this example right here. I'm going to create a circle just like that, and I will create its radius, AB. And if we take the perpendicular line tool, we can create a tangent at point B. And to confirm that this point only goes through the circle once, I will take the intersect tool right here over point B, or the circle and the line, and it only intersects at one place, 0.56, comma 0.566. And that confirms that there is only one point that touches this line and the circle. Moving on to two tangent problems. I have a problem set up right here. There's a bunch of lines, but we'll be focusing on line segments J, K, L, and M, the ones in red. So usually this type of problems we'll try to have you solve for segment A, B. So we know that tangents are perpendicular to the radius at the point of tangent C, and in this case at point C and point D. And to prove that they are 90 degrees, I have this angle tool right here. A, C, B is 90 degrees, A 90 degrees, and B, D, A 90 degrees as shown right there. So that's all good. So since these are 90 degrees, we can use Pythagorean theorem to find out the distance or length of AB. So we know that BC and BD, K and J are 10.24. That is the length of the tangent to the radius. And even if you didn't know it was 10.24, you would take these 2 points and you can use distance formula to solve for the distance. And the radius should be given to you. So you can take this here, 10.24 squared plus 3.47 squared is equal to AB squared, and it should give you 10.81, or approximately 10.81. And to prove it, I will do it on the calculator. So 10.24 squared plus 3.47 squared is equal to 116.8985, and if we take the square root of that, 10.81. So you see they are the same answer. Therefore, we are good.